paper with you guys. So the title is Less is More, Fewer Interpretable Region via Submodular Subset Selection. And I will start with the background. So it's about the attribution algorithm. And image attribution algorithms are typically interpretable methods which produce saliency maps that explain which image regions are more important to model decisions. So there are two kinds of strategies, the white box methods and the black box methods. So for the white box methods, it primarily rely on computing the gradients with respect to the model's decisions. Some of the representative baselines are CAM, GradCAM, GradCAM++, and ScoreCAM. However, these methods all rely on the selection of network layers in the model, which has greater impact on the quality of interpretation. And for the black box methods, it assumes the internal structure of the model is agnostic. For example, Lime locally approximates the prediction of a black box model with a linear model, but only slightly perturbing the input. The HSIC attribution measures the dependence between the input image and the model's output through the Hybrid schemate independence criterion based on the RICE. However, there are some limitations of the existing attribution. So some attribution regions are not small and dense enough, which may interfere with the optimization orientation. So most advanced attribution algorithms focus on understanding how the global image contributes to the prediction results of the deep model when ignoring the impact of local regions on the results. And second, it is difficult to effectively attribute the latent cause of the error to samples with incorrect predictions. So for the incorrectly predicted samples, although the attribution algorithm can assign the correct class, but it does not limit the response to the incorrect class, so that the attributed region may still have a high response to the incorrect class. And how this paper contribute is that they want to find a way that sequentially attribute those pixels or patches. And they have two key novelties. One is the subregion division, and the second is the submodular function. And I will start with their problem definition. So what is a submodular function? They first define, suppose like in the images, either the pixel level or the patch level, we put them into a set. Let's say the set is called V. And we have two subsets, the SA and SB. Probably one of the set contains the optimal interpretable regions that we want. So given an element alpha, where the alpha is like the whole set except the SB. So the set function is a submodular function when it satisfies monotonically decreasing property. What does this mean? It means, for example, when we add a patch or pixel alpha, it has to contribute to the interpretation. So for example, if you already have no regions in this image, and the image is about a dog, so adding the dog's head will give a huge value. The second thing is that suppose we have two sets right here, SA and SB. When SA is union with the alpha, it contributes more than SB union with the alpha. And at the same time, B is a bigger set, which means at the very beginning, adding alpha benefit more, but at the end, the beneficial will decrease. So still with the dog's example, it means like if we already have the dog's head, then adding a tail or something else probably will not increase the total value too much. So the function measures like how good is my chosen set of regions. And this is called submodular because each new addition help less and less. So they also define like how image forms. So they divide the image I into a finite number of subregions, denoted as those I1 to IM. And the goal is to select a set S consisting of a limited number K of subregions in the set V that maximize the submodular function. And how they perform this? They perform this through two steps, like we said before. The first is the subregion division. So like each image we introduced before is divided into M subregions, which is denoted as the IM. And for traditional strategies, they typically divide the images into regular patch areas, but they neglect the semantic information inherent in different regions. And instead, this paper starts with an existing image attribution algorithm to compute the saliency map. So this is like A with the size of W times H for the corresponding class I, the images class. So following this, the paper will resize the A into n times n dimension, where its value denote the importance of each patch. So here is the diagram of the paper. So based on the determined importance of each patch, D patches are sequentially allocated to each subregion, and the remaining patch regions are masked with 0, where D equals to n times n divided by m. So this process finally forms the element set. And by the way, this kind of subregion division can be like integrated with the existing attribution algorithms like the KEM or LIME for those white box and black box scenarios. And the second contribution is that they define four submodular functions, and I will introduce them one by one. So first, for the confidence score, the goal of this score is to leverage a model trained by the evidential deep learning to quantify the uncertainty of a sample. So normally the neural network uses the softmax output to estimate the class probabilities. However, the softmax tends to be overconfident. So this idea is very similar to the temperature variable in the clip. However, instead of using that kind of manually defined temperature variable, this paper defines the EDL-based loss function, which is expressed as here. So for those notations, Y is the one hot label of the simple X, and E, which is the learned evidence produced by the network, capital F. And they also define a score using the Dirichlet strength. So it's the summation of each like class probability plus one, which measures the total evidence gathered for all classes. And let's see how these things can be integrated together. So in this case, what happens will as the grows. So it will grow if the total evidence grows, which means the model actually spread its prediction over all of the classes. So this term and loss will grow, right? And we are doing the gradient descent, which a larger loss is a bad thing. So this term penalizes the model for putting too much evidence everywhere, especially like for those wrong classes. And for this term, let's say if the model is uncertain, so all of the EK are small and S star is small, but so the EC, so this term, like the loss will still remain high if the model is uncertain. And if the model gives the evidence to too many wrong classes, the Dirichlet score still becomes large, but the EC doesn't keep up. So the loss keep grows, which is also a bad thing. So if the model puts strong evidence into the true class and little on the others, that way, like the numerator and denominator balance, so the loss gets minimized. So this is how this function balanced the confidence and the uncertainty. So it's called the confidence score. So again, like the softmax only produce the normalized probabilities, which is bad. And the model want to leverage the EDL to improve the confidence. So when the model is unsure, it simply produce no confidence everywhere. Okay, and let's see. So for actually, let me take a look. Okay, so let's still understand this kind of thing. However, like the Esther is, we still need to use this kind of thing. So that is during the time of all class presents, right? And we can obtain those per class evidence. So here, like at the inference time, what's happening is, so Esther is the total evidence, the summation of all of the evidence we see before. When Esther is large, then the denominator is large, right? U is small, meaning it's not that, it's low uncertainty. Yes. And like if the Esther decreases, which means the total confidence decreases, then U approaches 1, meaning the high uncertainty. So what we want is high uncertainty, right? And by the way, this is the Esther. So the paper again expanded. So we the high confidence happens like when there is a large total evidence for some class. When the reverse, like the no confidence means the little evidence. And why this matters is because this kind of image attribution strategy can prefer regions of an image that the model is confident about. So this actually helps ensure that the selected interpretability regions are in distribution rather than out of distribution. And in effect, it filters out those unreliable evidence and stabilizes the attribution. And that's about the confidence score. Also, like the second part is about the effectiveness score. So the goal of this score is to maximize the response of valuable information with fewer regions, since some image regions have the same semantic representation. How it achieves the goal is just for an element alpha. This strategy will measure its distance to all of the elements in the set. So pairwise the distance here and take the smallest distance. So if alpha is very close to some element S, which means it may be redundant because we want every time we add the alpha, it will have the diminishing returns. It will have the return that larger than the previous one. So if the alpha is very close to the element in the set, it means it's redundant and we are pretty much sure we don't want this. And if the alpha is different from all of the elements in the S, then the minimum distance will be large. So effectiveness score is large. So this matrix rewards the element to add the new information compared to the set. Yes, and example about this score is that suppose we have two patches, both show sky. Their feature may be very close because they are representing the same object. So adding the second one gives the small effectiveness score, which is redundant. But like if we add a patch, let's say it shows a dog or the tree that's far away from the original object sky, then the effectiveness will be high because it's adding the new information. And the third part is about the consistency score. So the earlier, like the effectiveness score favors the diverse regions. So it want to spread out all of the features. But one bad thing is that could accidentally pick regions that are diverse, but not semantically relevant to the target concept. For example, it will select a background noise instead of the object parts. So previously we have the sky and the tree, but we indeed want to predict the sky. At this case, like selecting the tree will be a bad example. And this is why they want to they want to develop this consistency score. And it's basically a cosine similarity between the feature vector of the combined selected region and the target semantic feature. So let's see how to interpret this score. Let me see, I should have one slide. Yes, so again, like very similar definition as IF, we say that before. And the small fs is the target semantic feature, which is the feature vector representing the semantic goal. Well, I guess later it can also be a classifier, so a classifier for that class if we are doing the classification, right? And its goal is the cosine similarity. It tries to minimize the similarity between the feature vector of the combined selected regions and the target semantic feature. And how we obtain this? Yes. So one is from the original image. For example, we use the feature extractor to extract the embedding of the global image and the selected regions. This way, we expect the selected regions to have the similar representation as the global image. And in the classification setting, it can also be a classifier layer if we are working for the specific class. And finally, they designed this collaboration score. So the motivation is that some individual elements may leak significant individual effects in isolation, but when placed within the context of a group or system, they exhibit an indispensable collective effect. So let me think one example. So still with the dog. A dog's ear patch alone might not strongly indicate that's a dog, but together with the dog's eye, nose, or those things on the dog's head, that can reinforce the dog's concept. So this is the motivation of this collaboration score. Patches has to work collaboratively in order to help the DNA to make the downstream task. And in a high level, it's still a similarity. And those notations are things that we say before. So how this score works is that from an image, if we remove a region, then that decreases the similarity. So larger loss, high collaboration score. So this is a simple idea. Okay. Let me see. It seems like these are repetitive. Yeah. So here is the summary of the full score, confidence score, which ensures the selected region come with high predictive certainty. Effectiveness score ensures the selected regions are diverse, no redundant. Consistency score ensures they match the target semantics. And the collaboration score ensures the group of regions has the collective importance, not just the isolated effect. And overall, they combine this kind of full score into a overall function, which they call this as the submodular function. And recall from the beginning, like we expect the submodular function to have two properties. That is, when we add the patch, so the first is that it has to be monotonically non-decreasing, right? So every alpha, every added region will help. And second is that when we add this to a smaller set, it will benefit more than we add this to a larger set, which means we are selecting the important things at the beginning. And the goal of the theory is to explain that the model's prediction use the few image regions that are certain, no redundant, on topic for the class and jointly important will satisfy the two properties in the submodular function. And as a high level, like this is a high level proof sketch, like how they want to prove this. So as the method itself, it split the image into the candidate subregions, choose at most k of them to maximize the set function. And this turns the attribution into a subset selection problem. The key is to define F so that is submodular, like dimension returns and monotone. Never hurts to add a good region. So the overall theory will have two lemma to prove this. One is for this formula, like it's monotonically non-decreasing, and second for the second formula, like it's it has the diminishing effect. So because this kind of thing is it has four components, then the theory needs to prove them one by one, and I will go over them. So here is the confidence score, which we say is 1 minus k over the Dirichlet score. And for the first one, monotonically increasing. So it oh, by the way, I just realized like the subtitle of this lemma are reversed. Like, so dimensional return is for lemma 2 and that the monotonically increasing is for lemma 1. So how they prove this is that they try to plug in this formula. So basically plugging it here, plugging it here. That way you can get this formula. One gets canceled out. And as the first term is that SA plus alpha. So the paper leverages the Taylor expansion, which expands the formula. So SA plus the first derivative times alpha. That's the Taylor approximation. And also like because that is in the exponential function, so it can write out by 2 multiplication. So as alpha is small, because we are adding very small regions at one time, so this kind of alpha approaches to 0 from the positive way, from the positive axis. So if it decreases to 0, then e to the, so this one becomes 1, right? E's power of 0 becomes 1. Yes. And that way, the paper claims that it's indeed approaching the 0, but from the positive way. So adding alpha doesn't hurt. And similarly, I just realized this dimension returns is indeed correct. So similarly, like if we plug the same thing into the SB, right, we still get the 0. And two things that's approaching to 0. So something approaching to 0 minus something approaching to 0. That's approximately 0. That proves adding the alpha every time on a small set A indeed benefits. And lemma 2 still like with the similar formula. So this becomes 1, right? If it becomes 1, actually the denominator will be a bit larger. So that the second term be a little smaller than the first term. So the minus gets to be positive. So this means like adding the alpha indeed benefits the overall confidence score. And for the effectiveness score, it's the pairwise the distance. And how the paper want to introduce the proof is that when we add an element alpha, because it's a summation, we are basically adding a new term which tries to find the minimum distance, right? From all of the F alpha and Fs. And a motivation is that some existing elements in the set S alpha may now find alpha closer than their old nearest label. So their nearest label distance shrink in this case, which means, let me see. So this should be the original term, right? Should be the original term before we add alpha. And this is the term that after we add the alpha here. So it's the union with the alpha. And by this motivation, by removing alpha, actually we are probably removing a very small constant term. So that's why the paper minus a constant here. And on different set, this kind of proof applies. So similar for set B, we get the same thing. And as the motivation stated before, like more elements can potentially switch their nearest label to alpha. So the sum decreases cannot be smaller. The intuition is that with more elements in the set of B, there are simply more chances for alpha to become someone's new nearest label. So that's why, because B set B is bigger, subset A is a subset of the subset B, so it's bigger. That's why even it's two constant, the constant B is still larger than A. And if we have this, we minus these two terms, right? And we can get the set A with the effectiveness score, it will be larger than the effectiveness score of the set B. Okay, that proves the diminishing returns because adding the element to subset A helps. And now we want to prove the monotonically increasing. Sorry, this is a typo here. And similarly here, what we want to do is to, when we add an element alpha into set A, with the effective score, we minus the original one. We see before, like it's very equivalent to the original score where we minus a constant. And that this is probably larger than zero, right? Both are larger than zero. So which means adding the alpha will help with the effectiveness score. It's increasing. So that concludes the proof of the effectiveness. And the third score is the consistency. So it's the similarity here. What the paper did is it replaces the numerator with a variable for simplicity. So like this is the formula that we want to prove, and these are same. So the numerator gets replaced with the GSA, denominator the same, but they simplify that to be the norm of FSA and the norm of F. And still with the Taylor expansion for the previous term, because we are adding in alpha here, its expansion is the original point plus the first derivative, the gradient multiplied with alpha, similar for here below. And like, let's say if alpha is very small, close to zero from the positive side, so the denominator becomes the same, right? Because alpha gets to zero. And we minus the numerator where we can get the only different term is the gradient G of SA multiplied by alpha. So that's how they get this one. And even through this one, this is very small. So it's approaching to zero. Okay, so similarly, as long as we know like it's approaching to zero from the positive term, we replace subset A and subset B gets the similar results, and two limits approaching to zero when they minus, it's approaching to zero. So this gets proved. And also like when we add alpha here, which is exactly this formula, although it's approaching to zero, but it's from the positive side, so larger than zero. And this way it proves like it's a diminishing return from this slide, and it's monotonically increasing from this slide. Okay, and similar for the collaboration score. So I guess like cause both terms are cosine similarity, so the proof scratch is very same. They just replace the numerator to be a term, which is gi minus sa. And similarly, with the Taylor expansion, those terms gets canceled out, which will remain this kind of term. But the rest is the same. So I yeah, it's similar to the previous one. So I don't have a slide to go over the details here. And finally, we proved that the four terms here are satisfying the two conditions for submodular terms. First is that adding the alpha helps with the four scores. So they help with the interpretation, also help with the submodular terms at the end. Second is that when we add the alpha to a smaller set SA, it will benefit more if we add it to a larger set SB. So it has the diminishing return. Later, its return is small. That way, we can have the submodular function here, which also satisfies that two terms. And by an existing theory, which I should have a reference here, but it's a theory from the previous paper. So if S is the solution obtained by the greedy search approach, like how we optimize this, right? How we find this kind of these subsets, and S star denotes the optimal solution. Then the greedy search approach will exhibit the following approximation guarantee. So because we don't know like how we find the optimal subsets, and just by greedily selecting each patches one by one, each elements one by one, it has to be larger than 1 minus 1 over E of the optimal solution. It means like if we are using a greedy search algorithm to find the subset, the minimum guarantee is that we will have 64% of the patches that satisfy the optimal subsets. So this is the theory, and also the algorithm they use is to do the greedy search with that guided by that four scores. And here we go to their experiments. They evaluate it on three data sets. So two human face data sets, Celebar A, VGG phase 2, and one old data set, which is CUB 200 back in 2011. For Celebar A, they randomly select 2,000 identities from the validation set and one test face image for each identity. For the VGG phase 2, they randomly select 2,000 identities from the VGG phase 2's validation set and one test face for each identity. For the CUB 200, they randomly select 3 samples for each class that is correctly predicted by the model and 2 incorrectly predicted samples for each class from the validation set. How they set up the evaluation is through two AUCs. The deletion AUC, which means the change in class probability as important pixels or patches actually are gradually removed. And second, the insertion AUC, which is the change in class probability as important pixels are gradually added. So the image is perturbed to calculate the value of deletion or insertion of the proposed method. And by the way, this is a figure that's presented at the beginning. I find like when I transfer the slide, the video gets bricked. So yes, this is actually the video. how their algorithm works empirically, let's say. So first, they have two parts, right? The second part is the full score that we just see, and the first part is that they want to find a division algorithm. So HSIC, which is the black box image attribution algorithm in the background. This is algorithm here, and they try to combine this with their strategy. And this figure, I will interpret it later. But let's say a dynamic view is that the important pixels here get selected first by the greedy selection algorithm. Okay, so here is the enlarged figure. What they what they're setting here is that they take the images that the classifier mispredicted from one of the data set, probably not the face data set. So it's the CUB data sets because there's no face here. And they try to find which regions that first support the ground truth class and second cause the mistake. So this is their big problem setting. And they evaluate each method by first, the highest ground truth evidence it can reach when allowed to review only a fraction of image, and B, the AUC, the confidence that we gradually review the pixels. Okay, so um, okay, yes. So if the blue curve, right, the integration with the strategy that proposed in the paper races sharply at small and peaks higher than yellow, which is all of the cases here. So it's increasingly uh, very fast. That means their selected regions quickly drive up the ground truth confidence with only a small portion of the image to be reviewed. So every time here, like it's only 0.2, between 0.2 and 0.4, just with this proportion of patches, the blue line reaches the peaked value. And the area under the blue curve, which is the insertion AUC, is larger, which means the method is more feasible to what the model actually uses for the true class across the review levels. Okay, same thing here. And also, like in their experiment design, they try to integrate their method with the baseline, and all of the value gets increased. So this is the baseline comparison here. And because they have lots of attribution terms, so they try to launch an ablation study that first add one score at a time to see what's their performance, and second, do some combinations of this score and show their performance until finally they activate all of the four scores where the performance get reaches the best. So those four terms are functioning individually, like they all contribute to the method. Also, like they validate if the using of the existing attribution algorithm, the first contribution is important. So they try to the final one is to use the black box HSIC attribution, integrate their method with that kind of strategy. But they also try to selecting, basically follow the traditional strategy, I guess, to select those kind of different patches with different patch sizes. And indeed, like the strategy has to work with the HSIC or work with the existing image attribution algorithm, where HSIC attribution is an example that they show here. And here are the takeaways. So this is in attribute the paper proposes in attribution strategy. And this kind of strategy can, for correctly predicted samples, find fewer regions that make the model predictions more confident. And for incorrectly predicted samples, find the regions that caused the model to predict incorrectly. And this paper, which is called the less is more, involves two contributions. One is the subregion division, which it will work with the existing attribution algorithms. And second, it has the submodular function design, which contains four parts. Confidence part, so don't pick the uncertain regions. Effectiveness, don't pick the redundant regions. Consistency, pick the thematically correct regions. And finally, collaboration, pick the regions that together make a real impact. So this is the end of the presentation.